Hello, today I am going to discuss about the rest part of the design of shear connectors, then I will be going to discuss on purlins. In shear connector, last to last lecture I have discussed different aspects on the design and the codal aspects on shear connectors. Shear connectors we know are used when two different type of materials are used, means as a composite section when we are going to use in a member, then shear connector will be required to join each other. As I told in last to last lecture that we have to transform the section, we have to find out the I section or area in a transformed area, all this we have to find out. So, how to find out all these things I will demonstrate through the workout example, through which it will be clear. Then how shear connectors are going to design, how many number of shear connectors will be required to design such steel concrete composite beam will be demonstrated. So, at the first I will discuss about the composite beams, means composite members with special reference to composite beams. Why composite beams are advantageous, what are the advantages and what are the disadvantages, those things very little I will discuss here, because I am just going to give you an small overview of the composite beams. Composite structure is a separate things which will take 40 lectures at least to cover the composite structure, which is out of our syllabus. But with having a small introduction to this, you will get interest and you may do at your own to find out some other type of design of composite members. Right. Now, let us see what are the advantages of steel concrete composite beams. I have just written down here, just you can note that one is the most effective utilization of steel and concrete is achieved. Most effective utilization of steel and concrete is achieved, because if suppose there is a beam which is deflecting like this, then at the top the compression will develop and at the bottom tension will develop. So, if we can make something like this, say this is concrete which is taking care the compression, and if this is steel which is taking care the which is taking care the tension, because tension is developing here and compression is developing at the top. So, we can take the advantages of the property of the material and then we can make it utilized. Second advantage is keeping the span and loading unaltered. A more economical steel section in terms of depth and weight is adequate in case of composite beam, right, compare with conventional non-composite beam. Means if we use steel concrete composite beam, then we can find a more economical steel section, right. As the depth of beam reduces, it enhances the headroom. So, with the use of steel concrete composite beam, we can enhance the headroom. Another advantage is because of its larger stiffness, composite beams have less deflection than steel beams. So, as we know, the deflection depends on F is equal to K into D, where K is the stiffness, D is the displacement or deflection, F is the force. Now, if K is high, then definitely D will be less, because D is equal to F by K, right. So, because of larger stiffness of the composite beam, what will happen, deflection will be less. That is why for a longer span, if we can use composite beam, then we can restrict the deflection. That means restrict the deflection means the codal provision is given, that is the span by 325, that deflection means that we can keep our deflection within that allowable deflection, that is L by 325. Composite construction is amenable to fast track construction because of using rolled steel and prefabricated components rather than cast in situ concrete. So, this is another advantage when we are going to use composite construction. encased steel beam sections have improved fire resistance and corrosion. If the steel beam section is encased in concrete, then definitely the fire resistance can be improved, corrosion can be reduced, because we know the steel is can corrode, means steel is if it is exposed to the air, then the corrosion will take place. So, that can be reduced if we can use encased steel beam like things, right. And now, when we are going to use steel concrete composite section, we must know what are the disadvantages also. It is not that always we will get all advantages. So, if we know the disadvantages, then we can think whether we will go for composite section or not, right. In case of steel beam, means steel concrete composite beam, the disadvantage is that additional cost for shear connectors and their installation is required. So, we have to use shear connectors for joining the steel concrete composite section properly. So, additional cost due to the shear connector will be required, and for lightly loaded short beams, this extra cost may exceed the cost reduction on all accounts. Means, if the load is light or if the span is less, then unnecessary we did not go for steel concrete composite, because in that case the cost, overall cost will be increased because of the installation of shear connectors and other things. So, unless it is heavy load and longer span, we do not need to go for composite. So, we have to see whether it is really required or not. On that basis, we can find out that on the basis of requirement, the sectional dimension and how much steel dimension is required, means what is the dimension of the steel is required and what is the concrete is required, on the basis of loading condition and the end condition of the beam, right. Now, this is some typical picture of steel concrete composite beam. So, this is a concrete slab, this is reinforced concrete slab, this one, and this is a steel beam. So, steel beam and concrete means RCC slab has been connected together through this shear connector. Then shear stud is here, it is given, these are the reinforcing bar, these are the steel bar in different directions. So, this is how the steel beam interact with the supporting concrete slab. So, this is how we have to design this portion, we have to design properly with the help of shear connectors. Another case of if it is encased, steel beam is encased in the concrete, this is the concrete section, concrete slab, and this is the steel beam. So, this is another option through which the steel concrete composite beam may be made. Both the section, these are the two different type of section, both the sections have their own merits and demerits. So, we are not going into details of all those, right. Only thing we should know that this type of things means we use in the construction. Now, I will go through one example through which we will be able to understand how to find out the properties of different sections, how to combine those things, and how to analyze the steel concrete composite beam, then how to provide the shear connectors. Say design a composite beam with flexible shear connectors with the following data, right. One is the center to center distance of beams supporting slab, that is 2 meter. Then says length of beam means span, say 4 meter. Then say thickness of slab so let us consider 100 mm, right. Thickness of slab means concrete slab, right. Then say uniform load, total uniform load, total UDL over the beam, say 25 kilonewton per meter. Then say grade of concrete, let us use M15, and say modular ratio say equal to 18. So, these are the data we have. So, let us solve the problem. So, first what we will do, we will find out the maximum bending moment, because from the maximum bending moment we can find out the section modulus, and maximum bending moment will be WL square by 8, as the end condition has not been given. So, let us assume that it is a simply supported beam with having L span and W is there. So, if we put those value, W was given as 25 kilonewton meter and L was 4. So, this is becoming 50 kilonewton meter, right. So, we can find out the section modulus. Section modulus will be Z, that will become M by sigma BC or sigma BT. Now, we do not know whether the beam is laterally supported or unsupported, but it is not told. But when it is encased with when it is a composite beam, means when the slab of the concrete slab is connected with the beam, we can assume that it is laterally supported. So, sigma BC and sigma BT value will become 165 for FY 250. So, if we put the value, this is 50 kilonewton and then sigma BC is 165, right. This is for 0.66 Fy as we know, and Fy let us assume 250. So, if we assume Fy value of 250, then this sigma BC will become 165 and this is 50 kilonewton meter. So, I am multiplying 10 to the 6 to make it Newton millimeter. So, after calculating this, we are going to get the value as say 30303.3 millimeter cube, right. So, this is the value we are going to get. Now, from IS handbook number 1, that means SP6, from there we can find out the appropriate section. So, let us use say ISMB 250 with an weight of 37.3 kg per meter. So, we are using ISMB 250, right. So, from this now we can find out the properties which we require, that is say IXX, this is given, that is 5131.6 centimeter to the power 4, area is given 47 4755 millimeter square, and overall depth will become 250 because ISMB 250, and width of the flange is 125 millimeter, thickness of the flange is 12.5 millimeter, thickness of the web is 6.9 millimeter. So these are the things we can find out from the IS handbook, that is SP6. For ISMB 250, the corresponding properties can be write down. Now what we will do? Now we have to find out the width of the composite flange. Width of the composite flange. Composite flange, and that will be, it will be, width of the composite flange will be minimum of the following. As you know, that has to be decided from the spacing of the beam and other things, like say this will be L by 4, it has to be. So L was 4 into 10 cube by 4, and this is becoming 1000 millimeter. And another, from another point of view, that will be half of the spacing, means center to center distance of beams supporting slab was 2 meter. So 2 meter means 2000 millimeter minus the B value is 125, the flange width. So this is becoming 937.5 millimeter, because if we see the beams are placed like this. So these are 2 meter. Now slab is there, so either half of these two or another is B3, that will be 8 into slab thickness, that is 800 mm. So out of these three we have to find out the minimum one. So effective width will be, effective width of the concrete slab, this will become minimum of 100, 937.5 and 800. So minimum is 800 mm. So effective width of the concrete slab will become 800 mm, right. So now we have to find out the properties of composite section, right, properties of composite section. So how do we find out? Say property can be found out. Now let us draw the figure. So this is the effective width, which is 800 mm. We find out this is concrete slab, RCC slab. Then the beam is given, right, okay. This is the steel beam. Now this width is 125 mm, right, and other things are like this is given as 250 because ISMB 250 we have used, and the slab thickness is given 100 mm, right. So these are the properties we know, right. So now we have to find out the combined properties, property of the combined section, right. So first we have to find out where is the neutral axis depth. Neutral axis depth of the composite section. We know neutral axis depth of the this section is here, this concrete, and neutral axis depth of the steel beam is here at 125 from bottom, right, and here this will be 50 from top, and here this will be 125 from bottom, right. Now we have to find out the value of neutral axis, say n. So if we take moment area about this top flange, right, from here, then we can find out, say 800 into 100 the area, right, by 18 modular ratio I am making, right, because I am finding out the values in terms of steel. So the properties I am changing into steel. So this is the transformed area, remember, of the concrete, right. So into this will become 50, because 50 is the CG distance, plus the area of I beam is 4755, which was given in the IS handbook, into 100 plus 250 by 2, that is 125, right. So area into CG distance, right, by, so this is divided by, we can find out 800 into 100 by 18 plus 4775, right. So from this we can find out the value of n. This will finally will become 140.45 millimeter, that is from top, 140.45 millimeter from top, right. So neutral axis of the combined section is somewhere here, right. This will be 140.45, right. So this is how we got the neutral axis. Now we can find out Ixx about this, right. So Ixx will become 5131.6, that is the moment of inertia of the I section, into 10 to the 4 per millimeter cube, plus AR square, that is 4755 into R square. R square means this will be 125 plus 100, then minus 140.45, because this will be the distance from here to here we have to transfer, right. So we can find out total distance minus this, right. So 125 plus 100 minus this will be the distance between CG of individual I section and CG of combined I section, right. So AR square, then this is the moment of inertia about the combined section, plus for steel, plus for, we will calculate for the concrete one. Concrete one will be 800 into 100 cube, BD cube by 12, right, into modular ratio, that is 18, because always you have to transform the section in terms of steel, plus AR square, that means 800 into 100 by 18 into R square. R square means 140.45 minus 50, because this will become, this is 50, so this will become 140.45 minus 50, because this is 140.45, right. So this transfer has to done, so this is becoming A into R square, right. So if we calculate this value, we will finally find out value as equal to, say 12537.26 into 10 to the power 4 millimeter to the power 4, right. So Ixx we got. Now we have to find out Zxx. means Z. Here Z will be different because it is not at the center. So, y top and y bottom will be different, right. So, say Z top will be Ixx by y top. So, this will become Ixx is to this one 10 to the 4 by y top. Y top will be from top the distance is 140.45 neutral axis distance, that is here given it is, this is the distance, right. So, after calculating this we will be getting value as 892 into 10 cube millimeter cube, right. Similarly, Z bottom will become Ixx by y bottom. So, if we put those value, Ixx is 12537.26 into 10 to the 4 by y bottom. Y bottom will become say 250 plus 100 total depth minus 140.45, that is the neutral axis depth from top. So, the distance will become this one. So, if we calculate this value, so Z bottom will become 598.294 into 10 cube millimeter cube, and Z required we have calculated earlier, that is m by sigma bc or sigma bt, that was 303.03 into 10 cube millimeter cube, right. So, this is all right because Z top is coming as 892 centimeter cube and Z bottom is coming 598 say centimeter cube, right. Now, required is 303 centimeter cube. So, this is quite okay. So, we can say that the section whatever we have chosen is quite okay from the moment point of view. That means, the section whatever we have chosen is quite enough to carry the load which has been given. So, now what we will do? So, now shear connector, right. So, as you know VH will become AS Fy by 2. So, area was given 4755 and Fy is 250 we are using. So, this is becoming 594375 Newton, right. Now, let us provide say 16 mm diameter of studs, right, and let the height of studs is equal to say 100 mm. Let us use these two. Then we can find the H by D ratio as 100 by 16, that is 6.25, which is greater than 4.2. As per the Coral provision, it has to be greater than 4.2. So, it is okay. Now, Q will become 1.518 into 100 into 16 root over 15, right. This is the FCK value. The concrete we are going to use this one. So, this is becoming 9406.7 Newton, right. So, number of studs will become 5, the total force is 594375 by 9406.7, right. So, if we make it, that is coming 63.18, which can be made 64. So, number of starts will be required 64. So, if we use say 2 starts in each section, with a spacing of say 4D, then this will become, so spacing will become 4 into 16, 64 mm, right, and the longitudinal spacing of stud, this will become 4 into 10 cube by 2 into 1 by 64 by 2, right. This is becoming 62.5, which is less than, this has to be less than 4 into Ts thickness of slab. So, that will be 4 into thickness of slab is 100. So, that is 400. So, this is less than 400. That means this is okay, right. So, we can say that provide say 16 mm studs at a spacing of, say we are getting 62 mm center to center in 2 rows, right. So, in this way we can find out the values. So, a typical example I have gone through which we can find out a suitable section of the composite section, and then how to find out the number of studs or number of shear connectors, right, for that particular case. So, in this way you can make it. I hope this example will be helpful for designing composite section for other cases. Now, I will discuss about design aspects of purlin. Purlin, as we know, when the industrial sheds are designed, the wind force coming into picture at a particular direction, from a particular direction it used to come. So, when we will be designing a purlin, what we will see, purlin is basically a type of beam. We will see it is having two type of load. One is gravity load, which is acting vertically, another is wind load, which is coming from horizontally. And again, purlin is not about x axis or y axis, it has some slope. So, basically we have to change the loading direction, loading condition, then we have to find out what is the exact load coming vertically on the purlin, and then we have to design. Purlin may be used with the channel section or I section or angle section, right. Let me draw a figure of purlin from which we will be able to clear how the load is acting on the purlin. Say for an industrial building, say one I section is there, right. So, I sections will be acting like this, okay, and here the cleat angle will be there. This is called cleat, to keep in a proper position, right. Now, one will come force from this direction, another is vertically because of the gravity load, that is say P. So, the slope whatever we have here theta, that will become here also theta. so with an angle of theta. Now, if we give some direction, say this is UU axis and this is say VV axis. Okay. So, what we can do here, that MU can be find out from here. How do we find out MU? MU means in this direction we have to find out, right. So, what are the load is coming along this, that we have to find out. That is, first is H, this is coming, and another is P, one component of P, that is P cos theta, right. So, this is the UDL load we have perpendicular to UU axis, and then L square by 10. Purlins are considered continuous. So, accordingly the coefficient 1 by 10 are used for calculating the moment. So, the moment will become MUU is equal to H plus P cos theta into L square by 10. Similarly, MVV will become, there will be no component of H in this direction, right. So, only component will be P sin theta. So, P sin theta into L square by 10. So, this is one sort of moment, another sort of moment is this. Now, when we are going to find out the stress at a point, say stress at a point here, what we will find out? Say sigma BC or sigma BT, we have to find out for MUU and for MVV. So, here I have to find out IUU and here also I have to find out IVV. Then again the distance, say U and V, right. So, it will be a combined stress. So, all these things how to calculate, I will just give an overview of this. So, what I was telling, that purlins are beams provided over trusses to support the roofing. The wind force is assumed to act normal to the roof trusses and the gravity load pass through the center of gravity of the purlin section. Hence, the purlin section is subjected to twisting in addition to bending. Such bending is called unsymmetrical bending. So, such bending is called unsymmetrical bending. So, chances means the unsymmetrical bending cases will happen. So, I have to find out accordingly the stresses, right. So, in short, I will discuss about the design aspects of channel and eye section, then the angle section. I will not take much time to discuss all this, because if we want to go for discussion, then other things, other lectures will not be able to complete. So, here I will just give an overview, so that the students can design the purlins at their own with following procedures. So, for designing, first what we will do, that the center to center distance of adjacent trusses is considered to be the span of purlin, right. So, we know that purlins are placed on truss. So, center to center distance of trusses will be considered as a span of the purlin. Then the gravity loads P due to sitting and live loads etc., and the load H due to wind acting perpendicular to the plane is computed, right. So, gravity load and the wind load will be computed on the purlin, how it is coming, at what angle, at what intensity it is coming, that we will calculate, and then we will find out the moment, right. The loads act as shown in figure, that means the figure we have shown here, where the load is acting. In this way load are acting. Other type of purlin, if we see, say suppose if I extend here, we will see, say if we use the channel section. So, purlin will be like this, right. This is a purlin, and cleat angle will be given like this, right. Another is, say angle section, when we are going to use, generally we provide like this, right, and cleat angle will be like this. These are cleat angle. Right. So, these are also another sort of section which we are using for purlin, right, and loads as we shown here, in this way it will act. Now, next step is the maximum bending moments. The maximum bending moments MUU and MVV along these axes are calculated. What I have shown there, that MUU will be equal to H plus P cos theta into L square by 10, and MVV will become P sin theta into L square by 10, where H is the, if purlin is provided here like this, so this is I section, we are considering H normal to this direction. We are assuming that wind force is coming normal to the purlin. So, H will be this one, and P, what is P? P will be the gravity load. So, always it will be downward, means along y axis, global y axis. If we make like this, if it is x and if it is y, then global y axis, right. So, P is UDL along vertically and H is UDL along UU axis, means that axis in this is UU axis, means not along H will be along VV axis, we can say VV axis, or perpendicular to UU axis, and L is the span of the purlin, right. So, now we can find out the bending stress in a purlin, which can be determined from this equation. As we know that if we have a section like this, say I section, right, sorry, this is the I section. Now, suppose we are going to find out stress here. So, what we will do? We have to find out what is the distance in this direction and what is the distance in this direction, right, along UU and along VV, if this is U and if this is V, right, and I have to find out IUU and IVV, means in globally we can say IXX and IYY, which is given. So, for a particular section we know IUU and IVV we know, which is given in SP6. So, from there we can find out, right. So, sigma B, the stress due to bending, can be find out from this equation. Now, whether it will be minus or plus here, that depends on the direction, right. Whether it will be developing tension or compression, that depends on the direction of the forces, and where we are going to calculate, it depends on that. So, now if I make in terms of sectional modulus, I can write MUU by ZUU plus MVV by ZVV, because ZUU can be written as IUU by V, because IUU is in this direction and V is in this direction where we are going to calculate. So, this is ZUU, this is ZVV, right. So, sigma B can be written in this way, MUU by ZUU, if we take common, then MUU by ZUU into 1 plus MVV ZUU by MUU ZVV, right. So, in this way we can find out sigma B, the bending stress at a particular point in the purlin, right. Now, similarly ZUU also can be find out from this equation, that can be written in terms of this, that is MUU by sigma B into 1 plus MVV by MUU into ZUU by ZVV. Remember, ZUU terms is here also. What we used to do? We used to consider a ratio of ZUU by ZVV, then we can find out the value of ZUU. It is a trial and error process, right. So, next what we will do? So, what I was telling, that you see, for the I and channel section, a suitable value of ZUU by ZVB is assumed to compute the value of ZUU from equation B. Equation B means this one, right. To find out a suitable section for channel and for channel and I section, we can assume some ratio of ZUU by ZVB, then we can find out the value of ZUU, right. Then we can provide a suitable section. The bending stresses are increased by 33.33% to account for wind, right. The bending stresses are increased by 33.33 to account for wind, that also we have to take care, right. Then what we will do? Then we can find out the maximum bending stress from equation A. Maximum bending stress, which is given in this equation, that is MUU by ZUU into 1 plus MVV ZUU by MUU ZVB. So, from this we can find out the maximum bending stress, right. Then what we will do? Then we will calculate the value of bending stress. Okay. The calculated value of bending stress should be less than the permissible value of bending stress, which is this. Permissible value of bending stress has been considered as 1.33 into 0.66 Fy, right. 1.33 into 0.66 Fy. Now, similarly, we will discuss about the design of an angle section for using as a purlin, right. In angle section, it is an unsymmetrical section. So, in both the directions, the moment has to be calculated. In IS 800 1984, it permits the use of angle section as a purlin, provided slope of the roof truss is less than 30 degree. So, if slope of the roof truss is less than 30 degree, then IS code has permitted to use angle section also. So, angle section means, if we see, say if I see the angle section, the complication we will be understanding that if we see in globally, say this is XX and this is YY, right. This is XX and this is YY, and so bending may come in this direction also, which is VV, and bending may come in this direction also, UU, right. So, because loading is not from particular direction, loading is in two direction, means we can make it in perpendicular to that section and along that section. So, the unsymmetrical bending will occur, that is why we have to take care accordingly. Now, design of an angle section purlin. So, following procedure is adapted for design. The procedures similar way we can discuss, that is the vertical and wind loads are determined. First we will find out the wind load and the vertical load due to self weight and other imposed loads. Then these loads are assumed to be normal to the roofs, right. If roof is there, then wind load is assumed to be normal to the roof and vertical load will always be there. So, we have to take the component of that, right. And then after taking component of that, we can find out the maximum bending moment, which is WL square by 10 or WL by 10, where W is UDL load and this W may be used as concentrated load, that is given here. W is the concentrated load at centroid and this small w is the uniformly distributed load, right, and L is the span of purlin, right. So, in this way we can calculate the value of maximum bending moment. The moment we calculate the maximum bending moment, we can find out the required section modulus. The required section modulus will become m by 1.33 sigma b, m by 1.33 sigma b, where sigma b is the permissible bending stress, right. So, required section modulus when we are going to get on the basis of maximum bending moment, then we can find out a suitable section. The suitable section can be find out from IAS handbook, that is SP6. Whether we will go for equal or unequal, that depends on the designer's experience and the requirement, right. What is the slope, how it is, so on that basis we have to decide, right. Now, assuming the depth as 1/45 of the span and width as 1/60 of the span, a trial section of the angle purlins is arrived, right. So, how do we arrive the trial section of angle purlin? That is, we may assume depth approximately as 1/45 and width we can assume approximately 1/60 of the span, right. So, the moment we find out this approximate depth and approximate width, then we can find out a trial section of the angle purlins. So, depth and width must not be less than the specified values to ensure the deflection criteria. Now, in codal provision the deflection criteria is given, so we have to ensure that also that the depth and width must not be less than the specified values, right. Then a suitable section is then selected for the calculated value of leg lengths of angle section. The modulus of section provided should be more than the modulus of section calculated. Modulus of section provided means Z provide definitely has to be greater than the required, Z required, which is calculated from the moment, and this we have provided. So, in this basis we can design the purlin. Now, I will demonstrate a software very quickly which has been developed by my students. The objective of demonstrating this software is to show how quickly one can design a beam. Another thing is, if you see this software, then you will be able to design at your own. You will be able to develop the software thinking in mind that in this way one can develop a software easily, right. So, in the software what we have done, that first one GUI has been made where the type of load has to be told, type of load and of course their end condition, like different conditions are there which has not been, I am not able to show here because of shortage of space. There is, say, suppose cantilever with concentrated load at the free end, cantilever with UDL, simply supported with concentrated load at the center, simply supported with UDL. That means all the possible cases which we have discussed earlier, those has been taken care in type of load. Then the load means when we are going to tell type of load, after that what we can show the what is the load, whether UDL, if it is UDL then what is the magnitude, if it is concentrated then what is the magnitude and where it is, then the span length, then bearing plate length, right, bearing plate length will give, then what is the yield stress, yield stress list is given, when you click this you will get yield stress and then you have to analyze. So, these are the input which has to be means which is required for designing of a beam. So, after that what we will do, here you see just I am showing when list I am asking to show, they are showing the list what are the available type of steel we have. So, on that list we can choose a certain type of steel, right, and these are the results which you will get, means what will be the maximum bending moment, what will be the maximum shear force and what will be the section modulus of the section to be chosen. Means from the load, span and end condition you can find out the maximum bending moment, and this will display here, and you can check, means user when are using they can check also step by step whether the software is giving correctly the results or not. Then analysis report you will get, that suitable section for design means it will take the suitable section from the IS code automatically, where the data of IS code, that means SP6 data, has been entered in the program and stored there, right. Then depth of section what is required, width of flange what is required, thickness of flange what is what is there, means the details of the section which has been chosen, sectional area, thickness, everything has been chosen. Now you see, so from this we can find out with a fraction of second, means fraction of minute, the result of the design of a beam. So what are the input we will be giving, that say this problem I am going to, sorry, again this slide I am. So now I will demonstrate the example which I have solved in my earlier lecture. In one earlier lecture I have solved with the problem, that is simply supported beam with UDL load. If you remember, that was given 50, load was given 50 kilonewton per meter length. So total load will be over the span will be 250 kilonewton, right. Then span is 5 meter and bearing plate length was given 100 mm. If you have attended that class, then you must have seen that these are the data which we had. Now from list also we have chosen Fy as 250. Then the moment we are clicking here, we will get the results, right. So results will be like this. When we are clicking in analyze, you will get the maximum bending moment is developing this, maximum shear force is developing this, and required section modulus is this. Now from this we are going to choose ISLB 400, means the computer programming itself is going to choose a suitable section which is ISLB 400, and the details of the section property has been given, like what is the depth of section, what is the width of the flange, thickness of flange, and sectional area and thickness of wave. And remember, when the report is giving, means when analysis result is giving and telling that ISLB 400, it is checking all the steps, then only it is giving the final results. So this is how we can use. It is a very simple software we have developed, through which one can design a beam, right. The whole thing can be shown here. You see the simply supported beam with UDL load with this data, and when we are clicking analyze, we will get all the required data here, right. So in this way one can design. The purpose of showing the software is, as I told, that the students can develop at their own similar type of software, where the input is very less. Only thing is, in background the lot of checks has to be done which was discussed. Now after checking, finally you will get this result. Okay. Now if we go through manually, then we may not get the economic one, the most suitable one, but in software we will make the logic in such a way that economic one will get. So in today's lecture what we have seen, first we have discussed about the design aspects of composite beam member, and we have gone through one workout example through which we have seen how to find out a suitable section and how to find out the shear connectors details. Then we have seen very briefly the purlin aspects, means design of a purlin in case of I section and channel section, and in case of angle section also, what are the difference, we have just given an overview. Then which can calculate a suitable section to withstand that much load with that end condition and beam, right. So with this I like to conclude today's lecture. Thank you very much for your patience.